couple of things to think about normal distributions is they ultimately begin with a histogram. But this is a histogram unlike a sample that you can't collect. So imagine if we had an extremely large population of scores. And just as an example, just to give you something to wrap your mind around, let's talk about IQs. Supposedly, we all have IQs, which is this kind of innate ability to learn, or however you want to buy into that. I've had 10 IQ. Actually, I think I've had 11. But I've had 10 or 11. I've had a bunch, let's put it that way. Now, I've never scored the same thing yet. So I have no idea what my IQ is, but I assume it does exist, okay? Well, if you think about IQs for every single person in the United States, we have, our population over 300 million now, you couldn't go out and collect that data. First of all, it would be just certain constraints like time. But we know that those scores exist in theory. Therefore, the histogram of those scores exist in theory. We can't collect them, but they exist in theory. Now, we could go out and get a sample and do a histogram on the sample scores and get something maybe bell-shaped and symmetric. But guys, we're moving into a different dynamic here. We're moving into a histogram for an entire population, which can't be collected physically, but can be thought about theoretically. Well, nevertheless, if we could go out and collect scores on IQs for everyone, there are certain types of histograms that are not only approximately bell-shaped and symmetric, they are perfectly bell-shaped and symmetric. And when we smooth these things out, we don't, like a bell-shaped and symmetric distribution, get something approximately symmetric and approximately bell-shaped. We get something that can be thought of as being perfectly bell-shaped and symmetric. Now, we typically, when studying distributions like this, we don't draw the histogram. What we look at is we just look at the drawing on a horizontal axis, pretend that's straight, and we look at just the distribution itself, just the curve, not the bars of the histogram, but we're always thinking there is a histogram that's underlying this. Okay, so this distribution, so to speak, just represent frequencies. Well, it turns out that distributions, normal distributions, are completely defined by their mean, mu. Now, guys, remember, we're defining populations here. So in the previous video, I gave you notation for populations. So smack dab in the center of this distribution is the mean. And then there's a value right here that represents the spread around the mean, which is called the standard deviation. And in populations, we let that value be equal to sigma. Now, I think it's going to be helpful to let you see how, and let me explain what happens with this standard deviation. If you've ever had any calculus, you probably have studied the second derivative, and there's a point right there where if you trace this distribution, if you drew it correctly, you'll notice that we're kind of, we're coming down here, and then all of a sudden about right there and about right here, there's a place where that distribution almost takes on like a straight line. If you can come to the center of that straight line and drop an axis down, this is actually defined as one standard deviation above the mean. Now, I'm going to explain that a little bit better here in just a second, because I know that was probably a little bit confusing, but I'll explain it through some examples, okay? So the best way to think about this is let's just say we've got an axis here, and let's run this axis from 0 to 10 to 20 to 30 Okay, I'll stop. That was annoying. And let's just run it up to 100. And let's just see how these distributions behave with different means and different standard deviations. Guys, I need to make sure I'm recording. just, I may have pulled a goofy one. Yeah, I am. Okay, cool. So the first situation I want to look at, what would a distribution look like that had a mean of 30 and a standard deviation of 5? Well, the first thing we know is this distribution is going to be centered at 30. So I can draw a vertical line right there. And the standard deviation of 5 says that flattening out of the distribution, that line, is going to happen right here, 5 above and 5 below. Now, what do I mean flattening out? Well, where this thing takes on kind of a linear form happens 5 units above and 5 units below. Notice you're curving, you're curving, you're curving, and then all of a sudden you get a place here where it's almost a straight line. If you come to the center of that straight line, drop down, and this isn't drawn perfectly, then you get a situation where you can define what the standard deviation is. Now, let's contrast that with, say, the same mean of 30, but with a much larger standard deviation. Well, we still got our focus on the center at 30, but our standard deviation of 15 says we have to go 15 units above, and we have to go 15 units below. So what's going to happen here, to make that dynamic happen, we have to flatten out our distribution and get a normal distribution that looks something like this. Guys, you get normal distributions in all different shapes, sizes, and fashions. The higher the standard deviation, the flatter the peak will be at the mean. We can contrast something else. Let's say we have a mean of 50, standard deviation of 10. Well, that tells me that my distribution is centered at 50. And I'm going to go 10 units to the left and 10 units to the right, getting a whole lot of stuff going on here. And I just kind of feel this thing out, how this straight line thing is gonna happen here. And guys, I'm not going to ask you to sit around and draw normal distributions or anything. I'm just doing this to give you an indication of how the mean and the standard deviation define the distribution. So, very important. In fact, we're going to get into a bunch of stuff that's very important from here on out. A normal distribution is completely defined by its, well, that shouldn't be there. That should. Its mean and its standard deviation. Now, someone tells me, well, I got a distribution that has a median of 50 and an IQR of 20. Okay, cool. I can't tell you anything about the normal distribution. I must know the mean. I must know the standard deviation or the variance. If I know the variance, all I'd have to do is take the square root of it. But it is complete. The normal distribution is completely defined by the mean and the standard deviation. Now, I talked about IQs before, and IQs are normally distributed. This is going to be really cool for those of you that are in the social sciences. You probably know this. IQs are normally distributed with mean, mu equal 100, and standard deviation sigma equal 15. Now sometimes we abbreviate this and shorten out all of that stuff and just say IQs, draw a squiggly line, which tells me that approximately, put a capital N, which represents the normal distribution, and I give two numbers. The two numbers represent the mean and the standard deviation. The mean always comes first and the standard deviation comes second. So when I see that, I think mu sigma, so the mean is 100, the standard deviation is 15. So sometimes we abbreviate things instead of writing it out, so we can go spend more time on Instagram and things like that. All right, gang, so what that tells me, it tells me that I have a normal distribution. Some of you are going to get really good at drawing these. Some of you won't. That's cool. If we want to draw one, for an important reason, we'll use technology. So I know smack dab in the center of this distribution is 100. Now I know what happens over here. I know that I start about right there. Starts going straight right there. About the middle of that is right here. I'm going to drop a line down. I know that distance right there is my standard deviation. So I know I have to add 15 to 100. So the value right there would be 115. Now once I define that measure, I come up that exact measure right there, and I have two standard deviations above the mean. Then I can come on up and go 3 standard deviations above the mean. I could go 4, 5, 6, 7, 8, 9, 10. But typically when we draw a standard model, a normal model, a normal distribution, we just go 3 above and 3 below. Because of perfect symmetry, once I identify this, I can come straight across, drop down the line, and I know this has to be 1 standard deviation below the mean. Keep the same distance, 2 standard deviations below the mean, and 3 standard deviations below the mean. Again, I could go 4 below, 5 below, 6 below, 7 below, and so on. But I don't do that typically when drawing one of these models. Now, so a couple of things. Properties of normal distributions. First property, perfectly bell-shaped and symmetric. About mu. So these things are centered, they're all about the mean. You ever have one of those friends that's kind of like all about themselves? Well, the normal distribution is all about the mean. Completely defined by the mean and standard deviation. You got to know both of them to know what distribution you're dealing with. If you don't know both of them, you can't do anything. Okay? Area equals 1. So look at the area underneath the curve. That's just think of that as 1 unit squared. And the fourth thing, the x-axis serves as a horizontal asymptote. Now guys, an asymptote is just in mathematics, it's just a line that a graph gets closer and closer to, but it never touches it. So when you draw your normal distribution, if you draw it correctly, this line right here gets closer and closer and closer to the x-axis, but it never touches it. But you can use some fancy schmancy mathematics to show that even though it never touches it, it does have a finite area of 1 square unit. Guys, we got a kind of a neat property with normal distribution. 68% of the data will be between 1 standard deviation below and 1 standard deviation above. So guys, in general terms, the mean goes there. The mean plus a standard deviation goes right there. The mean plus 2 standard deviations and the mean plus 3 standard deviations. We could go on and on, but we don't. Here we have the mean minus a standard deviation, minus 2 standard deviations, and minus 3 standard deviations. It turns out that approximately 95% of our scores in a normal distribution will be between 2 standard deviations below and 2 standard deviations above. 99.7% of the information in a normal distribution will be from 3 standard deviations below to 3 above. And if you think about it, if we describe 99.7%, We're still missing 0.3%, aren't we? And 0.3% as a decimal is 0.003. Well, that's what we get down here in the tails, half of that. So we would have 0.15% in the left tail, and we would have 0.15% in the right tail. Now, guys, if your percentages, decimals, and conversions aren't really up to snuff, what we're saying here, 0.15% is equivalent to 0.0015. So that's about 15 out of every 10,000. That's what we mean by that. So gang, for IQs, we're saying that about 68% of the people have IQs between 85 and 115. 95% of the people have IQs between 70 and 130. Almost everyone, 99.7%, has IQ between 55 and 145. Not many people. Only about 15 out of every 10,000 has an IQ below 55. And not many people has IQ above 145. Only about 15 out of every 10,000. So if you're walking down the street and somebody says, you know what, I got an IQ of 152. They may. But and chances are they don't. You get all sorts of people. People get on like Facebook. They take those goofy IQ tests and then they run around and act like that that's what their IQ is. And again, guys, IQ testing isn't perfect. Again, I've taken 11 or 10. I don't guess it really matters. A bunch, and I've never scored the same thing yet. So now enter into something called a standard normal distribution. Now, what's the difference between a standard normal distribution and a normal distribution? Well, the word standard. And what does that tell you? That we want to do a distribution simply of z-scores. Well, gang, it turns out that z-scores form a normal distribution with a mean 0 standard deviation equal to 1. So we can always look at the standard normal distribution, which turns out to be an important tool in inference. We know that this will be centered at mean. It's mean 0. We know that this value right here is 1, 2, 3, and so on. So this is going to be -1, -2, and -3. Just like before, approximately 68% of the information in a standard normal distribution is between -1 and +1. So that would be z equal -1 to z equal +1. Approximately 95% of our information is contained from -2 to +2 and so on and so forth, just like before. Now, kinds of questions that your textbook gets into now is what proportion or what is the probability? Now, guys, in these types of problems, percentage, proportion, probability, at the end of the day, are telling us all the same stuff. What we're talking about in terms of this is really just according to the way that we work the problem. So let's say, for example, that let's just focus on the standard normal distribution. And again, this is a specific one that has mean 0, standard deviation 1. And let's say we wanted to find the area under the curve. Now this would have to be a negative z-score, because it's to the left of the center. Remember, we got 0 there, so anything left is 0. And we want to do this up to (0.28). So for reasons that will become clearer later, We want to find the probability of randomly selecting a z-score from this distribution and it falling between negative 1.4 and 0.28. So we could get fancy here and say, and ask the probability we could just get straightforward and say, what is the probability of randomly selecting a score that lies between negative 1.40 and 0.28. We could also ask what percentage of z-scores is between negative 1.40 and 0.28. We could also ask what proportion of z-scores is between negative 1.40 and 0.28. Guys, all of these are equivalent. In fact, they're so equivalent that I look for what's common, and what's common is what you're being asked starts with a P. Probability, whether you use notation or write it out, percentage, proportion. Well, guys, because of that, what I have kind of developed as a kind of a teaching tool is I have developed something called the P key. Well, I didn't develop it, but I had just kind of name it. And the P key is on your calculator, and this is the normal CDF key. And guys, the normal CDF key, for it to work perfectly, work correctly, you're going to have to put in 4 things. The last 2 are simple. It's the mean and the standard deviation. But the first 2 happen to be the lower bound and the upper bound of the area under the curve that you want to find. So for example, in the problem that I just gave you, we want in a normal distribution to find the difference between negative 1.40 and we want to find the area from that to 0.28. Is that what it was? Yeah, negative 1.40 and 0.28. So what goes here is the left bound, the smaller number, and what goes there is the upper bound or the right bound, which is always the bigger number, because these, guys, remember, this is the x-axis, and when we're on the x-axis, numbers to the right are bigger than numbers to the left, so the biggest number has to be right here. Now the way this was figured out, we're going from negative 1.40 to 0.28, so we're looking at that information between here. But regardless, the number to the left is always smaller than the number to the right, so the smallest number has to go here and the biggest number has to go right there. Well, guys, it turns out that the working these problems over here, regardless what form we're given, requires you to do the same thing on the calculator. Whether you're asked this, or ask it in words, or ask the percentage, or ask the proportion, you work the problem the same way. Okay? So let's see how we do that. So let's get out of here and let's take a look at on our calculator, because a calculator makes this really, really, really easy. Now, first thing I want to do is clear out the old stuff. All right, and there's a key right above VARS called DISTR. Well, it's in blue letters, so I have to hit the second function first and then come over and hit the distribution. Now, as I showed you, the key we want is the normal CDF, which is number 2, not the normal PDF. So come down to the normal CDF, hit enter, and okay, I'll tell you what, I'm gonna demonstrate both ways. I'll have to go get my calculator, the one that uses the. I don't think I have it here. Yeah, it's in there. So I'll demonstrate both of these. So this one right here, the lower bound is going to be negative 1.4. And the upper bound is going to be 0.28. I don't need to put the 0 in there, but you can if that kind of stuff turns you on. The mean is 0. The standard deviation is 1. So come down to paste. What it did is it takes that and it pastes it into the home screen. So you have to hit enter again to get the answer. So guys, our answer here is 0.5295. Now, depending on the way that you're asked to round this to 3 places, 4 places, and those instructions will be provided on Hawks, you would round accordingly. So if this says round to 4 places, you would put 0.5295. If it says round to 3 places, then you would use 0.530 because this 5 is going to bump up this 29 to a 30. If you're going to round to 2 places, it would be 0.53. So, rounding is the easy part of the class, so that shouldn't be a difficulty for anyone, okay? So 0.5295 is our answer from our calculator. So we go back to our, so depending on the way we were instructed to answer this, the answer there would be 0.5295, assuming we were round to 4 places. Same thing here for probability. Now, if we're asked percentage, we're going to put this in terms of a percentage, and the percentage would be 52.95%. And proportion is presented as, just like probability. Guys, it's that easy. Now, there's one caveat to this, or not really a caveat, but there's one thing that we have to be aware of. What do we do when we don't have, a number given as the upper bound, okay? So we have, let's say we have, again, z-scores form a normal distribution with mean of 0, standard deviation 1. Now we want to find the area under the curve that's above z equal 1.08. So essentially what we're doing here is we got this normal distribution centered at 0, and we want to come up here to 1.28, and we want to find the area under the curve all the way up to positive infinity. Well, it turns out you can do this. Positive infinity in our calculator is just going to be put in as E99, and I'll show you how to do that in just a second. So guys, to work this problem on your calculator, you're going to do the same thing. You're going to go second function, distribution, normal CDF. So the lower bound is going to be the small number, 1.28. We want this to run all the way up to positive infinity. Now guys, the way you do that, don't use the E from the alphabet. If you look at your comma, right above your comma, you'll see in blue letters or yellow, depending on your calculator, EE. That's the E we want. That's scientific notation. So I've got to hit the second function, E. Now, I only give you one E, but that's fine. And then I go 99. Mean still 0, standard deviation still 1, and we paste this, hit enter, and we get our answer is 0.1003. All right, So what I've done is I've just gone over here and I've answered the question. Okay. Now let's say we want to look at another problem. What's the area under the curve that's below 1.08? Well, you can work this one of two ways. One method of working this would be, Nadarbro said, that the area had to equal 1. Well, if I look at all this area below, I can use an ounce of common sense here and say that this area and this area has to add up to 1, and I know this area is 0.1003, so I know that this area has to be 0.8997. Or use your calculator. Now, what's going to happen here? If we're using our calculator to work this problem, we have 1.08. We want to run this thing all the way down to negative infinity. Negative infinity is the smallest number. It's not really a number, it's a symbol. But we would have to put this in first and the 1.08 in second. So, gang, to do that, if we decided to use our calculator, we would go in second function, normal CDF. Our lower bound is going to be negative infinity. Think of it as the smallest number, even though it's not a number, it's a symbol. Let's go up to 1.08. Mean is still 0, standard deviation still 1. Come down to paste, put it in, hit enter, and it's no, wait a minute, what's going on here? Oh, you see, you guys probably sitting there screaming at me. It's not 1.08, it's 1.28. So, I'll tell you what I can do. I can just go entry, since I've got everything right except for a typo, a bozo moment. That was supposed to be 1.28 because that's what I solved up here. Oops. Okay, so you see we get 0.8997, just as we said. Guys, hold on just a second. I'm going to show how the other calculator works too, just in case you have it. All right, gang. The other calculator works the same way. I've got it right here. Hopefully you can see that. It does the same thing. You still go second function, normal CDF, just like before, and you still come down to number 2. The only thing it'll do is this will direct you right back to the home screen. Now, make sure you've got that on the same, on a line by itself. Let's say you got some garbage in there and you haven't hit enter, and you go try to get normal CDF and try to put it there. It's going to give you an error because there's just too much stuff going on that line. If that happens, just start hitting clear, get back to a blank home screen, and get back to normal CDF, okay? So working the previous problem, what we would do is we would put in negative E 99, comma, 1.28, comma, 0, comma, 1, and close it up with the parentheses. So there's the list view kind of where you put, you just enter the numbers, and there's this one. And essentially they're doing exactly the same thing. So guys, just hit enter and you get this, the same value. Okay? So, again, just depending on the calculator you have. Now, we don't always have to have these problems for the standard normal distribution. Sometimes we can we can work other things. For again, just like we talked about earlier, IQs form a normal distribution with the mean of 100, standard deviation 15. Some studies are actually showing that the standard deviation is working its way more towards 16, and the mean is bumping up a little bit because we're apparently getting smarter. Either that or we're just becoming better test takers with all this testing stuff that we're putting students through today. But don't get me started on that one. All right, gang, so what we may want to do is we want to know, we select a person at random. What is the probability? Their IQ is between 80 and 105. Well, guys, that's equivalent to asking in this distribution. Now, guys, remember 80 is below the mean, so it's going to be to the left of the center. 105 is slightly to the right of the mean because it's bigger than 100. So this question is equivalent to saying what part of the area under the curve, when the mean is 100, standard deviation 15, is between 80 and 105. Well, gang, again, the calculator just makes it simple to do this. Just bust it out. All right. Normal CDF. So our lower bound here was 80. Our standard deviation is 105. Our mean is 100. And our standard deviation is 15. So we don't always have to have a mean of 0, standard deviation of 1. Turns out we will once we get into fancy stuff and study some central limit theorem and get into hypothesis testing. But right now, we're not there yet. So let's paste it. If you think about it, this is exactly what you see on the other calculator. You just type it in. You just don't have that intermediate screen. But anyway, the answer here would be 0.5393. All right. Don't you hope statistics stays this easy? It's going to get harder. But guys, we'll do it together. All right. Turns out ACT scores form a normal distribution. These parameters came from, probably about 2012, I do believe. I think the mean is bumped up a little bit, closer to 21, and standard deviations bumped up a little bit, closer to 5. But I think this was for 2012. But the ACT scores that year were approximately normal, mean of 20.4, standard deviation 4.8. So we could ask ourselves, what's the probability of randomly selecting someone that has an ACT score above 26? This is equivalent to find the area to the right of the curve at the point marked at 26. Now this gets into a little goofiness in a way. We're going to run this all the way up to infinity. And you're probably sitting there thinking, well, come on, Darbo, you can't get higher than the 36. I understand. Well, never mind. But, at the end of the day, let people, these psychometricians, people who modeled these distributions, this phenomenon, let them worry about that. Even though you can't have an an ACT of 40 or 100,000 or 3 million. There's not much area out there anyway, because of this asymptotic behavior. So we're still going to run this thing from 26 out to E99, long story short. So guys, let's do it. So we want to run this from 26 up to E99. Mean, don't forget to change the mean. Sometimes that's easy to do. 24.4 and 4.8. And paste that sucker in there and go for it. So our answer would be 0.1217. So guys, you can probably see why I call this the P key. The reason I call it the P key is this key, this normal CDF key, works problems for us that begin with the P. What is the probability of randomly selecting someone with an ACT above 26? 0.1217. What percentage of ACTs are above 26? 12.17%. What proportion of ACTs are above 26? 0.1217. Write it out. Use the notation for probability, 0.1217. So those problems work. Things that start with P: percentage, probability, P, proportion. Things that start with P, you can almost rest assured that you're going to use the normal CDF key on your calculator. Now, your book and all these textbooks, they give these goofy tables, these standard normal distribution probability tables. I think those are extremely goofy. To me, that's kind of like if you're going to go to Columbus tonight, you're going to take a horse and buggy. Those values are created by technology, so why not cut out the middleman and just use technology? But if you'd like to learn how to use one of those, I may put something up a little later and show you how to use those tables. But I'm not a huge fan of the tables. I'm just we've got the calculator, and the calculator created the values in the table. So why in the world would we use the table? All right, gang. I don't. Let me show you one more thing. I don't know if this if you care about this or not, but it's kind of cool. Where when you go to this distribution right here, you can see that you've got this option normal PDF. We don't use it to work problems, but we could. This is the long way. This is kind of like, let's say you want to work that previous problem. And let's go back to it. You want to work the previous problem. What's the proportion or probability ACT above 26? One way, the easy way, is to just use the normal CDF. Uh, 20.4, 4.8. I think that's what I said, right? Yeah. So we could use that. Another way is if you want to get elaborate here and actually get a picture and do some real fancy shading stuff, well, this next 2 minutes is for you if you want to get really fancy smancy. So what we could do is we could go into y equals, and let's clear out the stuff that we have there previously because we don't want that to mess around. All right. And I want to go into stat plot and turn those things off, where they're already off, so I don't have to worry about that. So what I can do when I've got my flashing thing there at Y1, I can go in here and get that normal PDF. Now, normal PDF stands for a normal probability density function. Now, we want this graphed across all x's, so we're going to let that be an x there, and we want to look at the distribution of ACTs, which have a mean of 20.4 and a standard deviation of 4.8. So we can paste that in there. And now if we go to our window, and let's think about what we want to do. We want to graph this thing from 3 standard deviations below the mean to 3 standard deviations above the mean. So I got 20.4 minus 3 times 4.8, so 3 standard deviations below the mean. And I want to run this thing from 20.4 plus 3 times the standard deviation. Now I want this to be 1, and I want this to be 0, and I don't care what you put here, just as long as it's a number above 0. Now what I can do is I can come in and do zoom fit. I don't know where zoom fit is. I'll have to go look for it. What zoom fit does is it'll take the X values that you gave and it'll adjust the Y's to give you the best picture. So if I go zoom fit, calculator's going to work a little bit and it's going to give you the most perfectly drawn normal distribution you have ever seen in your entire life. Okay, you know, there you go. There it is. Now, it doesn't work the problem yet, but it will. If you come in here, second function, distribution, and go over to draw and do shade norm. So my lower bound here, I want my shading to go from 26 up to E99. And again, I want this on the distribution. It has mean of 20.4 and a standard deviation of 4.8. And I can go draw, and what it's going to do is it's going to go into my distribution and it's going to draw out the area under the curve that coincides, and it'll give, as the area equal, it'll give you your answer of 0.1216 that we knew before. That's kind of cool. It's kind of a cool feature. You know, you could take a screenshot of this and get all fancy smancy and stuff, crop it out and do cool stuff. But so if you need something like that as a teaching tool, or even just because you like that kind of stuff, kind of like me. But guys, if you're pressed for time and you just want to get the answer, don't fart around with this stuff. Just come to this distribution, come to number 2. Normal CDF. Now, guys, if you try to mix the two, you're going to get into big trouble. So if you try to use normal CDF and you accidentally choose normal PDF, and you're like, well, my X value is, it's just going to give you an error. So, guys, just don't do that. Just go second function quit. You know what? I think I am done. Let's end this lecture, and the next lecture we'll get into. We'll get into more normal distributions. Guys, take care.